Okay, so we were talking about univariate versus multivariate approaches for modeling these things. The idea of when you have time-varying variables, letting the model partition the variance for you instead of doing group mean centering to do so. And so up to this point, I've presented these as choices that you get to make. So this is slide 5 in lecture 3. You could either do some sort of brute force variable partitioning that involves the person mean at level 2 to make sure that your effects are separated across levels. Or you can let the model partition the variance in X along with the variance in Y. And here are the pros and cons that we talked about with respect to that. Now, when do you not get a choice? When your time-varying predictors themselves show individual differences in change, you do not get a choice. It has to be multivariate. So in the example that we just had, time was irrelevant. There was no systematic differences in symptoms or stress or mood across the days. But if we think about the example that we started with yesterday morning, changes in risky behavior across age, the slope for time is a big part of that story. Changes across age in risky behavior varied across children. So we're also going to look at a time-varying predictor of monitoring. Well, do you think to the extent at which some parents increase their monitoring and some parents decrease their monitoring, that's going to matter too. So whenever there's just a fixed effect of time in your time-varying predictor, you don't need to worry about this. But once it has individual differences in change, then it has to be multivariate, and person mean centering is going to be wrong. The problem is that once you have individual differences in change, there's at least two kinds of between. The person mean is not adequate to represent between. It represents between intercept specifically. You might also need between person slope variance. And so you have to fit a model that includes random intercepts and slopes for your predictor in the same way that you would for your outcome. Otherwise, the level 1 residual effect is going to be smushed by having what the slope effect should have been. And the other implication of that is that if people change all the same, right, you can think about the intercept as mean differences and show that it doesn't matter what occasion it is, it's still the same set of mean differences. If people change differently, though, their rank order may change, such that where the intercept is going to mean something different. So what I'm talking about then, graphically, is the idea that just as we may have a random effect of time in the outcome, if we have a random effect related to time in the predictor, it has to be part of the model. And that predictor's time slope could be related to the outcome time slope in the same way that the predictor's intercept can be related to the outcome's intercept, and the level 1 residual can be related to the level 1 residual. So without this extra part on top here, without this level 2 slope variance and its effect being partitioned, it will be down here in the purple, and it will be another version of the same problem of smushing. And I did a simulation example in chapter 9 that demonstrates that conjecture. So does that make sense? If your time-varying predictor has individual differences in change, then it has to be treated as an outcome in order to make a slope variance for it in addition to the intercept variance. So this type of model, you can think of a lot of different ways. You can think of this as a bivariate latent growth curve model. You can think of it as a multivariate multi-level model. But the idea is that we have 3 piles of variance for each of our variables, and we can examine associations across each of those. So then we can have 3 options for how to estimate these models. We can trick univariate software into doing it so long as all of these relationships are phrased as covariances. But if we want them to be direct effects like mediation or anything like that, it has to be multivariate software, which means it can be this M plus between within, or it can be this single level structural equation model. And the single level structural equation model in particular has a lot of problems in how people set up time-varying predictors. So these are some other instances in which you would want to do multivariate models when you're looking at relationships across levels of analysis, as well as questions about differences in predictor effects. But just to make it a little more concrete, what types of questions you might ask. So we're thinking about multivariate relationships for variables that change over time. One might ask whether there are differences in their fixed effects. So for instance, if I'm doing a treatment study, I'm trying to cure depression. I might give 2 different measures of depression, and I might ask, does my treatment work better according to one measure than the other? Is there a bigger effect of time on one measure than the other? And that would be a difference in the fixed effects across outcomes. I would need both outcomes to be part of the same model to be able to answer that question. But a different question would be related to the random effects. So if I am higher than everyone else on my intercept, am I higher than everyone else on the intercept of the other variable? And the same for the slope. And so these are between person associations that you'd be interested in. So for example, here's some plots of individual trajectories. The heavy black line through these is the sample mean. This is an indicator of functional change, grip strength, and this is cognition block design, which is a measure of spatial reasoning, and these are samples of older adults. I might want to know if there's more change in cognition during this period than there is change in function, and I can answer that question if these variables were similarly scaled. But if I want to think about the idea of does it all go together when it goes, is this person who started out super strong over here relative to the rest of the sample, is that the same person who's super smart? And is this person who sort of fell off the cliff here, did they also fall off the cliff in cognition? So we have associations between the random intercepts across variables that are possible as well as the random slopes. Another example from my days at Penn State, looking at multivariate outcomes as 2 children from the same family. So if the older sibling increases over time in this is risky behavior, does the younger sibling follow suit? Are the random intercepts and slopes related across people from the same family? In fluctuation type studies, we might look at fluctuation in different kinds of affect and see if they go together. If somebody is super unhappy on this day, are they also likely to say they're super low in positive affect on the same day? And so that would be a relationship among the residuals. So in univariate software, fitting these models amounts to tricking it into thinking you still have one outcome and estimating all the random intercepts and slopes simultaneously. This is pretty straightforward to do in M+ as well, but you're looking for the covariances among these things as indications of relationships. More random effects you have, the more likely the model is to break. So that's a caveat to keep in mind when you're trying to do these things. In addition to between-person relationships, we can have within-person relationships of the residuals. So in this picture, for instance, there's a lot of noise here, but on average, the black outcome line here is heading up and the blue outcome line here is adding up. But after we detrend for those differences in change over time, at a given occasion, if my residual is off my line in one direction, is the residual for the other dB off the line in the same direction? So if you look at how these things sort of go together, this is the idea of residual relationship, or outcomes traveling together over time, as it's sometimes called. And so that's another way that these variables can be related. In order to properly evaluate these kinds of within-person relationships, though, you have to get the slope part right first. So there has to be, for each outcome that changes over time, a different estimate for the intercept variance as well as the slope variance. If there's nonlinear slopes, you would need between-person slopes and the variance in those two. So the residuals only make sense once it really is just the within-person information that's left, and everything that's between persons has been captured by the random effects. So then you could have a correlation across outcomes at the same occasion. In univariate software, it would look like that. So this is how you would do it if you were going to use univariate software. You would essentially stack your data again so that you have all of your outcomes in one column. You would have ID variables to keep track of which is which, And you would set up your model so that you have a separate set of fixed and random effects for each outcome. So that's what would work for you if you're just interested in looking at covariances across your outcome random effects and residuals. If you want to predict them, though, this isn't going to work. So that's what an equation would look like for a multivariate multi-level model, where I have the dummy codes DVA and DVB that function as switches. So they would control what fixed effects and what random effects and residuals go with each row of data. So I have examples from my class that use this sort of setup. I'd be happy to share those with you. I wanted to do more with respect to M+, but this is what it would look like in SAS. So these basic ideas are fairly straightforward. Between person-intercept relationships, between person-slope relationships, and between person or within person residuals. Now, how people actually implement that sometimes goes awry, particularly in the world of path modeling and SEM. So first, what not to do. And several of you have helpfully brought me pictures that are modern examples of this, so you don't have to look very hard to see models that look like this. So here's what not to do with respect to longitudinal data. The problem in these things that I'm going to show you is that all of these estimated paths are smushed to some degree. So there's this model. I call this the model that needs to die, otherwise known as an autoregressive cross-lag panel model. There's a recent paper that just came out that does a great job of explaining why this model needs to die, even though they stopped short of using that strong language. But as you look at this, each of these variables here is measured across 4 occasions, and they're interested in predicting last time's occasion to next time's occasion across variables. And so this idea of this, that's a cross-lag. And they have the residuals at the same occasion correlated as well. So the problem with this is that these paths right here are smushed. They're not between and they're not within. There's some mix of the two. The idea that you need to look at y1 predicting y2 before you can look at x1 predicting y2, this idea that you have to control for the previous occasion, what they're trying to do is to partition out between person differences so that you're left with just the within person. But to the extent that the correlation pattern within a variable is not autoregressive, you're not getting the between person stuff all the way out. So these paths reflect both stable individual differences in intercept, potentially individual differences in change, as well as time-specific residual relationships. Those are at least 3 distinct relationships that are all shoved into one of these paths. Yeah. So what's wrong with this model is that these paths right here, these cross-leg paths labeled as B3 and B4, there's only one of them. So there's B4, B4, B4. So what does that mean? Is it that people who are higher on Y are higher on X? Or is it when you're higher than usual on Y, you're higher than usual on X? Or is it people who change more on Y, change more on X? Those are 3 different things that it could be, and it's all 3 of them just smushed together. Logically speaking, if you're interested in how last time's whatever predicts this time, next time's something, that has to be a within-person association, because you're the same person all the time. So whatever between-person relationships there are in terms of constant individual differences in mean and slope is irrelevant for looking at within-person association between this time and last time. You have to be able to partition the between-person relationships out to see what's left, to be able to really look at these kinds of lagged effects. So don't do this, and don't do this either. This is the longitudinal mediation model. So it's basically the same idea. These things are smushed. We don't know what these A and B paths mean. So how do we fix it? Random effects or latent variables. So the models that we've been looking at are how you fix it. You can also fix it using latent variables in SEM, which folks here seem to be less interested in, so I'll skip over that. All right. So do you want to see how to fix it in an example that has nothing to do with SEM? Would that make you happy? Yeah, okay. Let's fix it. So let's pick up a new example. Number 4. And I do have SEM code in this example. We can just ignore it. If you don't like it, that's okay. I'm just trying to be complete. So this is the same day that we modeled yesterday morning. We modeled risky behavior changes across age. This is from chapter 9. It's made up data, but it's based on a true story. Here is on the left a spaghetti plot. Do you know that term? You took a handful of spaghetti and threw it at a wall. Like this is what it would look like. That's why it's called that. Again, if you're in a job talk, these are not spaghetti plots. These are individual trajectories. But as you can see, it looks like risky behavior is increasing across age, the extent to which varies across kids. At the same time, we also have parental monitoring at each age. And I generated these data such that there is no fixed effect of time. So on average, it's not that the average amount of monitoring is increasing or decreasing, but that at the individual level, there is a random effect of time. So some mothers are decreasing their monitoring as the kid gets older, while some mothers are increasing it. So both of these time-varying variables have individual trajectories of change that have to be part of the model. Even though I'm thinking about risky behavior as an outcome, and I'm thinking about monitoring as my predictor, I have to treat them both as outcomes so that I can estimate random intercepts and slopes and residuals. And here is a plot of the two against each other. So you can see sort of the overall shape of this, that there's a negative relationship between risky behavior and monitoring. So more monitoring looks like it lowers risky behavior, but within this pile, the individual trajectories have different slopes to them. So there's at least 3 ways that these two variables can relate to each other: in intercept, in slope, and in residual. Okay, with me so far? Yes? Residual. Why are you off your line today? So the residuals in these models would represent the difference between the trajectory that is predicted for you based on your random effects and the actual outcome. So if I am being monitored more than my trajectory is projecting at this current time, so if I'm relatively high, am I engaging in relatively more risky behavior at that same occasion too? So after controlling for between-person differences in change, is there a within-person association between these variables? That's another question one can ask. So here is the model. This is using something very close to what I did in chapter 9, but I actually added to it so that I could do a few more things with this example. So this is showing the way of writing this model using the dummy codes. So DVR is 1 if I have a row that's for risky behavior, and DVM is 1 if I have a row of data that's for monitoring. So in SAS, they're in the same row. In M+, they'll be in 2 different rows. So I have a separate set of beta placeholders for the intercept for each outcome, the linear slope for each outcome. Risky behavior has a quadratic slope, whereas monitoring does not, based on preliminary models. And they each have their own level 1 residual. Then at level 2, I have fixed intercepts and a fixed effect of parents' attitudes at age 12 on the intercept, as well as a fixed linear slope and an effect of attitudes on the fixed linear slope. I have that for risky and for monitoring. And then I also have just a fixed quadratic slope for risky. So it doesn't have a random slope variance, and it doesn't have a moderation by attitudes because our last model suggested that was non-significant. So then we're looking at how these U's relate to each other across outcomes, and how the E's relate to each other across outcomes. And so this example then examines 3 different ways of getting at those relationships, just as a bivariate latent growth curve model where you're just letting them be correlated, then as directed relationships within multivariate MLM as well as single level SEM. So, any questions before we dive in? All right, so here's the first one. This is just letting the random effects be correlated. So it's not predicting one from the other, it's just seeing if the random intercepts and slopes have a relationship. And I can do that in univariate software. So for instance, to do that in SAS here, I take a data set that was 1 row per occasion per person, and I stack it again so that it's 1 row per outcome per occasion per person. I have these DVR and DVM dummy codes that act like switches. When I put the fixed effects into the model, every fixed effect is attached to either the DVR or the DVM. So they look like interaction terms, but they're actually considered nested effects. So this, for instance, right here, that is the fixed slope of age for the RDV. This is the fixed slope for age for the MDV, monitoring versus risky behavior. If you take the general intercept out of the model, then you get separate fixed intercepts for each outcome by putting in the dummy codes instead. Same thing in the random line. On the M plus side, I'm using a stacked data file. I had to create an age squared variable to be the quadratic term myself already. So here's age centered at 18, age squared, attitude centered at 4, which is a time invariant level 2 predictor, risky behavior, which is my time varying outcome, and monitoring centered at 3, which is my time varying predictor. So I centered it at 3 so that 0 would mean something since it's going to be the predictor. Person ID is my level 2 ID variable. The only variable that is purely level 2 is attitudes. That's the time invariant predictor. The only variables that are purely level 1 are my age variables, linear and quadratic. So by not listing risky or monitoring on the within and betweens, I'm letting the model partition their variance. So here we go. Terms with an R are for risky behavior, terms with an M are for monitoring. So in the within model, here are my level 1 residual variances. The next 3 terms are placeholders that set up the linear time slope for risky, the quadratic time slope for risky, the linear time slope for monitoring. And then I have the residuals at the same age covary. So if you're off your line in risky in one direction, are you off your line in monitoring in the same direction? Do they travel together, so to speak? At the between level then, first off are my fixed intercepts for each variable, then their random intercept variances, the fixed slopes. So, move this one. I don't know why that shows up first. There we go. Linear, quadratic, and then the linear slope for monitoring. Here are my random linear slope variances and their labels. And here is the quadratic age slope variance that I have shut off. Next up are my level 2 fixed effects. I have attitudes as my time invariant predictor, predicting the risky intercept and the risky linear slope, as well as the monitoring intercept and the monitoring slope. And then here are all possible covariances among my random effects. So the first two are within a variable. So risky with R slope is risky's intercept with risky's linear H slope. Likewise, monitoring with M slope is monitoring's intercept with its linear slope. These are going to stay like this the whole time. No matter what else I do, the intercept and slope for the same variable get to be related. These are the relationships that will change across models to show you what happens when you specify them different ways. Right now, they're all covariances. So this is the covariance among the intercepts, among the slopes, one intercept with the other slope, and the other slope with the other intercept. Covariances are hard to interpret. Like if I said you have a covariance of 50, you'd be like, is that good? So wouldn't you like a correlation? Wouldn't it be nice if I could just be like, output STDYX? Will M+ let me ask for a standardized solution in these models? Nope. So I made one. So here's another use of model constraint. You'll see that I labeled each of my variances, and I labeled each of my covariances. And so down here, I'm computing their correlations. So the same thing that SAS would give me if I just asked for G-core and R-core, the correlation versions of those matrices, I have to make myself. So here's the formula. It's the covariance over the two standard deviations for the variables multiplied together. So there they all are. Any questions? All right, so let's see what happens. So this pretty much is the population model, by the way. I made these data. I know what they were supposed to happen. That's always comforting. So I have in bold over here from SAS the correlations that are going to show up at the bottom here, as well as all the fixed effects. So I'll focus on the M+ side. So there is a significant covariance between risky behavior and monitoring at the same occasion, meaning that if I am higher than predicted at a particular age and risky, I'm also likely to be higher than predicted on monitoring. And that covariance, when standardized, translates into a correlation of 0.35. Within level residual variances, then, those are level 1 variance. Why are you off your line today? Next up are the effects of attitudes on the intercepts and slopes, and then all of the covariances among the intercepts and slopes. The mean for R quad, what's that thing? Any guesses? Quadratic intercept, yes, I would call that the fixed quadratic effect of age. It calls it a mean because it's not being predicted by anything. Likewise, let's do this one right here. What's that intercept otherwise known as for R slope? It's the intercept for the slope, clearly, right? Now that's my fixed linear age slope for risky, listed as an intercept. It's under intercepts because it is being predicted by attitudes. In my equation, go back to that, it is right here. Gamma 1 OR, that's what that number is. So if you zero in on just this line for beta 1R right here, it looks like a little mini regression model, doesn't it? This one right here. And this first term that I call like the jumping off point for the slope, you can think of this as the intercept of the slope equation. And that's why they call it that, even though it's the slope. Yes.
So would that be the mean slope when we're attitudes are centered?
It is when, this is the linear slope when attitudes is 4, specifically. And that's why it's labeled as an intercept rather than a mean. See, quadratic age slope is a mean because there's nothing predicting it, meaning it's unconditional. Whereas this is conditional, it's specific to attitudes of 4. Yeah, so then this gamma 1, 1 would talk about how the slope increases per unit attitude. Or decreases, as it were. And here is the monitoring linear slope, which is not significant. And then last but not least, what would I call these level 2 residual variances? I would call them random effects left over. That's what I would call them. So these are left over after being predicted by attitudes. But they're not yet predicting each other. They're just covarying. So the 3 relationships that I'm most interested in here, I have the correlations so that you can get a sense of a standardized version. So ResCor is the residual correlation at level 1. The extent to which being off your line in risky behavior is correlated with being off your line in monitoring at the same occasion. I have an intercept correlation. So these are intercepts as defined at age 18. So girls who are higher in monitoring at age 18 than other girls are lower in risky behavior at age 18 than other girls. Say that again. Girls who are higher in monitoring at age 18 than other girls are lower in risky behavior at age 18 than other girls. And all parts of that sentence are necessary. At age 18 is necessary because that is specifically what the intercept means. And this number would be different if it were at age 12 or age 15 or any other age. Than other girls is necessary to convey that this is a between-person relationship. It's the rank order at age 18 on one variable related to the rank order on another variable. So it's a cross-sectional between-person relationship. And the new part, the part that cannot be approximated by person mean centering or by any other kind of brute force version of this, the correlation between the random slopes. So this one's negative, which would mean if I increase in monitoring more than other girls, I am likely, to a little bit of an extent, small amount, to decrease more than other people in risky behavior. And interpreting a slope correlation can be tricky because you don't necessarily know if it's an average increase or decrease that holds across all the people. So, in looking at the pictures, which can help convey what to talk about, I would refer to lesser or more increases. There's nobody in the picture who's decreasing in risky behavior. Whereas if I'm talking about the slope for monitoring, I could talk about increases or decreases because both of those are happening. So there's a negative relationship between the slopes, meaning that more positive in monitoring means either less positive or more negative, or excuse me, more positive in risky means less positive or more negative in monitoring. They go in opposite directions. The slopes?
Yeah.
The slope correlation, yes. If I grow more in risky behavior than other girls, I am likely to either increase less or decline more in monitoring. So it's an inverse relationship, just like it is at the intercept. So it looks like monitoring is good for you, right? Keep a handle on your kids and they're not going to go crazy, except when you handle them just a little too tight and then they go crazy once they hit college. So yeah, I set up these data to have both patterns in them. The idea that maybe people are being monitored more than usual at a given occasion because they merit it. So the within-person effect is positive. Or maybe they, because they're behaving badly, they get monitored more than usual. Or mom cranks up the monitoring and so they act out more than usual. I don't know which way it goes. But there's a positive association within persons, whereas there are negative associations between persons in the intercepts and slopes. So 3 different ways that these things can be related to each other. An autoregressive path model would not capture those 3 things. If I didn't have the slopes in the model, this relationship would show up as a bias in the residuals. The slope variance comes from the residual variance. So if I don't include it, the level 1 residual relationship would be smushed with the slope relationship. Okay. Questions? Okay, here's a picture. If you're fitting this model in your job talk, you need a picture. This is what we just did. It's a bivariate latent growth curve model. Bivariate latent growth curve structural equation model. And this is what it would look like using the SEM side of M+. Which, do we agree we still don't care? Is that the current consensus of those of you who are left? You wouldn't mind seeing it? It's like, don't hate me, guys. I'll go over this one real quick, because the others are going to look a lot like it. So SEM takes different data structure. M+ has something in it to flip it back to what we'd call Y, or separate variables for each occasion. So I'm taking my 3 stacked variables and telling it to make separate versions for ages 12 to 18, so that 1 row of data is for 1 person. Then I list the variables that are in the original file. The ones that are in the model are my new ones. This is the magic option right here. T-scores. Have you seen that one before? Nope. This tells M+ that time is unbalanced. And when you set up a slope, rather than fixing the loadings to represent the times, you can fix it at individual specific times. So for instance, in this picture, if I had balanced time, it would look like this, where the loadings convey the differences in time. 0 would be the loading for the age 18 occasion to the slope. -1 is 1 unit in time before. -2 is 2 units in time before, so this conveys linear. But this doesn't work for unbalanced data because not everybody is exactly 1 unit apart. So t-scores says take these loadings, instead of fixing them at constants, fix them at these variables. So age 12 holds the exact age for each girl. Age 13 holds the exact age of the next occasion, and so on. So that's why when we set up the growth curves, we're using these t-score variables instead. So here's risky. This bar syntax, it also understands as meaning I'd like a quadratic growth model, please. Only a linear growth model for monitoring. Here are all of the fixed effects. So the means of these latent variables are your fixed effects. Here are the random effect variances. Our quads get shut off the same as before. Here are the covariances within a variable between the intercept and slope. Here is attitudes predicting each intercept and slope. And here are the cross-variable relationships in intercept, slope, and the combinations of the two. And last but not least, the idea that the residual at each occasion gets to be related to the residual for the other variable at the same occasion. Level 1 is not in the model. Level 1 is a series of boxes. So risky 12 to risky 18, p-width, which stands for pairwise width, monitoring 12 to monitoring 18. So it correlates 12 with 12, 13 with 13, 14 with 14, etc. I am holding all of those covariances to the same number as if it were a level 1 model. So ResCov there makes all 7 of those things held equal. And then I am converting the correlations into covariances into correlations the same as before. So this line right here, this p-width line, that in a nutshell is why you would do SEM instead of MLM if you have the choice. Because not only can you have the same occasion relationship, but you could have 12 predict 13 and 13 predict 15. You have access to all of them at the same time. Whereas in the MLM, you only have access to the data that's on the same row. So if you wanted to have a previous occasion predict the next occasion, you have to shift the data to put the lagged variables onto the same row. Okay, does that help? Good, right. Any other questions on this? Okay.
I have a question.
Sure.
And even backing up a bit, how is the quadratic, so risky is quadratic, within a quadratic risky term. So how is that represented? Like, what is that conceptually?
Time squared,
And why?
because it needed to be bendy.
Okay, thank you.
Yeah, you wouldn't know it from staring at this, but M+ knows what you meant. It's kind of creepy. It knows the first thing is going to be an intercept, the second thing is going to be a linear term, and the last thing is going to be a quadratic. If you wanted to do a different kind of model, like piecewise or exponential or something, you would have to write more things than this line.
You throw in two categories. Another one that's cubic, and another one it's.
I don't know.
I think I've done at least two cubic before.
Okay, then it knows.
Yeah.
Well, there you go. Yes.
So just assume the first one's the intercept, the second one's the slope, and the third one's the quadratic, and use name, just keep it straight.
Yep, the names are mine. Yep. 8 characters or less, that's the only constraint. Other questions? All right. So this is the same model, you just get a whole lot more output. So it lists ons and then widths. And so note all the separate level 1 relationships. I've constrained them to be the same, but that's a choice. It would be a likelihood ratio test as to whether or not they should be the same or different. But this also shows you that you could have 12 with 13, or 14 with 16, whatever you wanted to have. On the intercept side, that's one piece of code I forgot to mention, all of the observed variables have to have their intercepts fixed to 0 so that the intercept factor can take over and hold them instead. And we have rint, rslope, mint, and mslope. Those are my fixed intercepts and fixed slopes. And then under residual variances here, what would I call that? Would I call that residual variance? Or would I call that something else?
What's left over after the random effects?
Not on this one, it actually is the level 1 residual. They threw it all in the same column. So there's no between versus within output here. This 8, that's the level 1 residual variance for risky, which you can see I have forced to be the same. That's another choice. This is the residual variance for monitoring at level 1. And then these last 4, these are the random intercept and slope variances left over. And then last but not least, here are my 3 correlations, which match exactly from the model previously. It's the same.
So the last 4 between subject, over there.
That's right. The last 4 are between subject random effect variances left over. One brief aside about fixing these variances to be equal. That's not the default in the program. You have to do that yourself. I would argue that it makes sense most of the time to start with an assumption that they're the same. The job of the random slopes is to make the variance change over time. So if you were to ask M+ to predict what the variance put back together again at each occasion is predicted to be, you would see it change over time. The random effects do that part. If the model for change fixed in random effects of time is properly specified, then what's left should have constant variance across time. If it doesn't, then you're probably missing a random effect step. So when you free these variances to be different, they're actually competing with the random slope variance to try and capture the same phenomenon of changing variance over time. Ready to move on? Okay. Now what if you did not want to have just covariances? What if you wanted to have directional relationships, such as a mediation model? let's change part of it, just the level 2 part, to see what happens. So this is back to the MLM side. The code is the same. I have a covariance at level 1 between monitoring and risky. The two things that I have changed are underlined here. I have swapped a with for an on. I am having the monitoring intercept predict the risky intercept, and the monitoring linear age slope predict the risky linear age slope. Because risky is covariated with monitoring at level 1, these intercept to intercept and slope to slope relationships are between. To try and get a sense of whether or not it's capturing what I think it should, I have code down here to create a pseudo-standardized effect for each of these. So in regression, single-level regression, it's easy to ask for standardized regression weights because there is only one Y variance and only one X variance to contend with. We can do the same thing here if we pay attention to which piles we should be using the standard deviation for. So in this case, if I want to create something like a standardized effect for the intercept predicting the intercept across variables, I would put their unstandardized effect here and use the square root of the X variable, which is monitoring intercept variance, and the square root of the Y variable's intercept. I stole these from the previous output. So I'm trying to create a standardized effect to see just how much relationship there is between the intercepts. And it should be the same number as what we got from the covariance. That's how I figured out which of these things are contextual and which of them are between. So here's what I get. See, I knew by this point we would all have lost our will to live. So I was like, make it easy on them. Look here. So these are my two new fixed effects. They're negative. They're significant. They're in the scale of the intercepts and the slopes. And if you look at their standardized version, sure enough, spot on. So the standardized effect of the intercept predicting the intercept is the same as the correlation between them. That's as it should be. So this is a check to see what the heck n plus is going to give me. So I know those correlations are between. So I know at this point the model is giving me between relationships for the intercept and between relationships for the slope, because they match the bivariate relationships if you just let them covary. Here's the SEM thing. Model 2B, changing one line. Right here. I should underline that. There we go. I have switched the level 1 relationship from a covariance to a directed path, monitoring, predicting, risky, but I've done it without a placeholder. I've done it directly within the level 1 model. What's going to happen is that the intercept relationship is still going to be between, but for reasons that I do not understand, the slope relationship switches to contextual. So now you get some of each. And I just figured this out last week. So this is breaking news. Because I was building this example, going, what the hell is it doing? Yeah, some of both. So here's some standardized effects, as well as some additional between effects. And just in case you wanted to do some sort of a mediation thing here, attitudes, predicting, monitoring, which predicts risky behavior. Here's X to Y of attitudes predicting the risky things. Attitudes predicting the monitoring as a mediator, excuse me. And here's the indirect effect of attitudes through the intercepts and the indirect effect of attitudes through the slopes. If you wanted to, you could also mix the two up. You could go attitude, intercept, slope, attitude, slope, intercept, and any combination thereof. So the between-person model has the potential to test mediation effects and direct effects. The within-person model does not, because there's only two variables. There's no X analog. So here's an example of how you would ask it to do those things. And so sure enough, the slope relationship now is very different than what it was previously. And that's because we have to add it to the within-person effect to get the between effect back. So the within monitoring to risky residual relationship plus the relationship between the slopes gets you to the between slope relationship that it should be there. Oh, and there's no indirect effects. But there's how you do it. Yeah, I just figured this out last week. For real. So, you're welcome. Here's how to get between effects using structured residuals. Does anybody care about that? No? Going once? Nope. Structured residuals in the CM. Yep. Nope. Okay. There you go. The last variant then. Now the placeholder. If you wanted to have the level 1 relationship be random or be moderated by a level 2 variable via a cross-level interaction, then you have to set it up using the placeholder. By invoking a placeholder to hold the level 1 relationship, it switches the intercept relationship to be contextual as well. Interestingly, no matter what I do, the cross-variable intercept-slope relationships, so monitoring intercept with risky slope, monitoring slope with risky intercept, those are always between. I don't know why, but they are. So here's my within-person effect. The mean of my placeholder is its fixed effects, and I shut off its random variance because we didn't need it in this example. And now we have a different intercept relationship. The level 1 residual relationship shows up in level 2. There's the between relationship when you add within to contextual, and there's the indirect effects, same as the previous model. So, moral of the story, I hate to tell you this, but you may have to run things a couple different ways to be sure that you know what you have. If you start with a model where everything just gets to be covariate, then you know how big the relationships should be at each level, And you will know when something happens to make them contextual instead when you don't get those same numbers back. So just in preparing this one example, I stumbled across all of these unique twists as well. Switch to this and switch to that. I can't even be sure that this is an exhaustive list of all the possibilities. So covariances will always get you between. Ons, that's where you sometimes stumble into contextual effects. Questions? More SEM, same thing. Skipping that since no one cares. Structure residuals to do a cross-lag model. So the idea of lagged effects. I've had a couple conversations with you guys. You do want to hear about lagged effects, right? Yeah, right, Neandri? Yeah, she's like, yeah, talk about that. So how to get a lagged effect is a more complicated question since M+8 came out. So in the SEM version, I did what's known as a cross-lag effect. I had the residuals at the same occasion covary, and then I had risky being predicted by monitoring at the previous occasion, as well as monitoring being predicted by risky at the previous occasion. So the picture that I showed you where I said, don't do it the wrong way, this is wrong. How I fixed it is by fitting random intercepts and slopes to Y and to X, so that these paths are purely within. So this part of the model, if it refers to the residuals, can be correct. The key is making sure that it refers to the residuals by putting either random effects or latent variables in that capture intercept and slope differences between persons too. Sure.
You said that a recent article had come out.
Yes, this article is on the front page of your syllabus as one of your suggested readings. So yes, we fixed it. So here's what this model gave me in terms of the lagged effects. It told me that monitoring does not predict the residual of the risky at the next occasion, but that the risky of the previous occasion does predict the monitoring of the next occasion. So it looks like there's an effect one way, but not the other. I'm here to tell you that this is a type 1 error. I did not put that effect in my data set. The contemporaneous effect that I did put into the data set is captured as a with. So the lagged effects are not controlling for the current occasion's relationship. So it's straightforward to do this in SEM. How do you do this in MLM? Well, I tried a couple different options to see if how I did it made a difference, and it did. So I did this on Tuesday of last week. So here's what we get if you control for the contemporaneous effect first. So I have monitoring predicting risky at the same occasion and monitoring predicting risky at the next occasion. The contemporaneous effect is significant like you would expect. Monitoring to the next risky is not. Likewise, if I go the opposite way, risky predicting monitoring at the same occasion, risky predicting the next monitoring, I get an even stronger cross-leg path. Type 1 error, but it's stronger. So what happens if I were to do this in MLM? Well, you've got a couple options. M+ version 8 has introduced a new set of code that I used here. I hadn't had a chance to play with this yet, but this is what it would look like. So I created another data set in which I added manually lagged variables as well, so I could compare my version of a lagged analysis to theirs. Their version uses this new command right here that goes in variable called lagged. You provide it with the variable that you want the previous row to be included and how many rows back. So if you wanted it 1 row, it's a 1. If you want it more than 1, you put a 2, and so on. So this is the version of the model that has a contemporaneous covariance paired with a lagged effect of previous monitoring predicting the next residual and next risky and previous risky predicting the next monitoring. And to refer to those newly lagged variables, they've introduced yet another special character, ampersand. They're going to run out of special characters pretty soon. They'll have to switch to like wingdings or something to specify your model.
You have a thumbs up emoji.
Thumbs up emoji, nice. So when you use this new lagged thing, I looked on their website and I could not find any documentation as to exactly how it works. It forces you to use Bayes. So I acted like the typical user and I didn't change a thing. I said, fine, make it Bayes. So I didn't mess with any of the other defaults that it would invoke in doing this. I just wanted to see if I would come up with the same answer as I did setting it up in SEM, where I know what I did. So here are the same models, 4 different ways. This is what I got, the first one here in SEM. So this is setting up a residual relationship as a correlation at the same occasions. And then these are the standardized paths from monitoring to risky at the next occasion and from risky to monitoring at the next occasion. So given that this came from SEM and that it used maximum likelihood, or I know what it's doing, I think of this as probably the rightest answer. This is one data set, but I think this is the one that I would trust the most, and I was interested in seeing how they compared. So if I do MLM and I lag my own variable, here's what I get. I get a completely different pattern of results. Noticeably, the standard errors are much smaller than I think they should be for the lagged variable. And I get a different pattern of significance completely. So that made me nervous. And I thought, okay, well, maybe my variable's messed up. Let's use their lagged variable. And their lagged variable with Bayes, which I love, they give stars for significance in Bayes, even though you're not supposed to say significant. Does anyone else find that hilarious? It's like, what? So yeah, their results agreed with my suspect results. This is, oh yeah, sorry, this is my lagged and Bayes, excuse me. So these two agreed across estimators. Here's theirs. So it looks closer for this one, but it's off on that one, and the standard errors are also too small. So it looks like my lag is wrong. The SEM way I trust the most. Their way is somewhere in the middle. But the fact that I don't get the same answer is disconcerting. And I can't run the SEM using Bayes to get a fully crossed comparison because you can't use t-scores in Bayes. So this is an open question as to what to do if you want to do lagged effects. If you have enough people and relatively few occasions, I would trust the SEM way of doing it, in which the lagged effects can be part of the same model where you have access to all the boxes. If you don't have that luxury, I would tread carefully. Sorry to end on a downer, but I don't know what to tell you. Yeah, sir.
I want to understand better what the red score does. So that rule out however much the residuals correlated at each time, both where you're predicting from and where you're predicting to.
That is just a bidirectional relationship converted into a correlation. So it's the ResCove standardized, and so that is agnostic as to direction. So when people fit these cross-lag models, that's typically what they do, is let the residuals from the same occasion just correlate, and then they have the lagged effects where they go 1 unit further in time. So I was trying to mimic that process, even though I don't necessarily agree with it theoretically. That part came out pretty much the same. Fairly close to the same answer for what that should be across models. It's the lagged effects that looked like they had different standard errors and point estimates to the point where they changed what was significant across models. That made me nervous. So there's supposed to be M+ version 8.1, which is adding some more stuff with this. I don't know if that will go better, but I just wanted to give you a cautionary note about lagged things. I don't know what's going on, but that makes me nervous that I couldn't find any documentation about it. And yes, I'm recording this, so maybe I'll get sued. That'll be fun. I'm pretty sure the mutanes sleep on a bed of money every night, so maybe they'll have pity on me. I'm training their customers. They should pay me.
So, would you say that the contemporaneous estimations that we've been working work out better than the lag?
It was more consistent across models.
Because you're comparing an X and Y variable with two variables maybe at the same time.
Yeah, the contemporaneous relationship is the one that I put in the population model. I didn't have any cross-lag paths. So if this were accurately recovering it, none of these would be significant. So it makes me nervous that I even have this here, but then to see the patterns switch according to different ways of setting it up is disconcerting. And here's the same thing after you change it from a contemporaneous to a directional, going from monitoring to risky, and then other way, going risky to monitoring. And again, you see differences. So, disconcerting. Particularly going this way. So, I don't know quite what to make of that. So, shall we take a break? I think yes. Maybe we can talk about generalized models when we get